Okay. All right. So, good afternoon, students. Good afternoon. So, we're going to get started. Now, just to sort of recap what we would have covered in our last session, we would have spent some time looking at gas laws. Yes? We spent some time looking at the gas laws, and we would have introduced one of the gas laws, which was Boyle's law, right? So we would have looked at Boyle's law. And before we even talk about Boyle's law in detail, we would have said that when we're looking at the gas laws, we see where the gas laws allows us to see the relationship between the properties of a gas, right? So with the gas laws, we're able to investigate the relationship between the properties of a gas. So we would have mentioned about Boyle's law, where we saw where Boyle's law shows the relationship between what two properties did we say? Pressure and volume, right? So Boyle's law shows the relationship between the pressure of the gas and its volume, right? Now, you remember, students, you'll remember students, would have stated that, with Boyle's law, we saw the relationship between the volume and the pressure, right? Now, remember we said that, there are three essential properties that, we will look at. The pressure is one, volume is one, and the temperature, right? Now, for Boyle's law, because we're looking at the pressure and the volume, we have to ensure that the temperature is what? Is constant, right? So, Boyle's law allows us to look at the relationship between the volume and the pressure, right? And we saw that there was a relationship between the volume and the pressure when we keep the temperature constant. Now, can anyone just remind me what Boyle's law states? Yes. Go ahead, Kiana. Okay, so we saw where once you have a fixed mass of gas, and again by a fixed mass of gas, we mean that the gas is enclosed in some container. So no gas can escape, first of all, and no gas can be added into the container. So once you have a fixed mass of gas and the temperature is constant, we saw where the volume was what? Inversely proportional, right? Which simply means that, if we increase the volume, what's going to happen to the pressure? Is going to decrease, and vice versa. So if we increase the pressure, the volume will decrease. Right? So that's Boyle's law. So increasing the pressure, volume must go down. Increasing the volume, pressure must go down. Right? So once you do one thing to the other, the opposite happens to the other quantity if they are inversely proportional. Okay? Alright, so we're going to continue with looking at the gas laws, and specifically we're going to be looking at Charles' law, right? Charles' law, all right? Charles' law, right? So good way to remember it, Charles chocolates, right? So Charles' law. And again, each gas law shows some relationship between two properties of the gas. So we saw Boyle's law, we look at pressure and volume, right? For Charles' law, we're going to see that we're going to be looking at some relationship between the two properties. So let's start with that first of all. So for Charles' law, we look at the volume and temperature. Alright? Now we're going to now write a statement to define Boyle's law, Roger. We're going to now write a statement to define Boyle's law. So, yes, Charles' law. Yes, so we're going to write a statement to define Charles' law. So Charles' law, this states that and we always start with this statement, that for a fixed mass of gas, so we always start off with this statement. right, that we're dealing with a fixed mass of gas. Now we're going to now talk about the relationship between the volume and the temperature. So this states that for a fixed mass of gas at constant, so in this case, because we are looking at the volume and the temperature, what are we going to keep constant? Huh? The pressure, right? The pressure, because again, it's always the volume, temperature, and pressure we look at. Right? So if we're looking at volume and temperature, the third one, which is the pressure, will be kept constant. All right? At constant pressure, the volume of the gas is directly proportional to, and for this we want to pay keen attention, because yes, we're looking at the relationship between volume and temperature. However, the temperature that we talk about here, once we're looking at gas laws, is always what we call now the absolute or the Kelvin temperature. Right, the absolute or the Kelvin temperature. So what does that mean if we say the Kelvin temperature? What does that mean? Remember again, we're doing physics, and when we give something a name, we always choose a name that is meaningful. So if we're talking about the Kelvin temperature, what does that mean? Temperature measured in Kelvin. Right? So once we're looking at gas laws, we always want to ensure that our temperature is measured in Kelvin. Right? So if it is that you're given a question and the temperature is not in Kelvin, then you'll have to do what? Convert. Right? You're going to have to convert. And we would have discussed how we convert from Celsius to Kelvin from before. Alright? But we're going to be reminded of that as we go through. So that's Charles' law. Right? For a fixed mass of gas at constant pressure, right? The volume is directly proportional to the temperature measured in Kelvin. Yes? Alright, so that's Charles' law. And again, just as before when we were looking at Boyle's law, we're going to look at a mathematical statement that summarizes this law right here. So let me just give you a couple, a minute or so to just take this down, and then we're going to look at the formula. So that's the definition for Charles' law, right? Now again, we said that once we keep the pressure constant, the volume is directly proportional to the temperature, but specifically the temperature measured in Kelvin, right? So we can write that the volume V is directly proportional to what? The temperature in Kelvin. So we get V is directly proportional to T. And again, we can write this as V is equal to, we introduce the constant because we remove the directly proportional sign and we introduce an equal sign, so we have to attach a constant which we're calling KT. So V is equal to KT. And again, we can just make K on one side, divide both sides by T, so we get V over T is equal to K. So this right here now summarizes Charles' law, right? This statement right here will summarize Charles' law, because what this is saying is that the ratio of volume to Kelvin temperature is a constant, right? The ratio of volume to Kelvin temperature is a constant. And we can take that a little further to write this as V1 over T1 is equal to V2 over T2, right? So we will use this expression right here when we're performing calculations, right? So we'll use this to perform calculations. Now, we should be aware that V1 would represent the initial volume, right? And T1 would represent the, right? So V2 would be the final and T2 would be the final temperature. So again, this would be our expression. And again, once we start to look at calculations, we always want to ensure that we have the temperature in Kelvin, right? Always want to make sure that your temperature is expressed in Kelvin. All right, so we're going to look at a few examples, but before we look at the examples, I'm going to introduce some graphs that we're going to see when we, let's say we conduct an experiment to investigate Charles' law and we plot a graph with the results that we get. We're going to get either one of these two graphs, Ariana, that's Warburton. We're going to get one of these two graphs that we're going to be looking at. All right, so let's look at that now. So we're going to talk about the graphs associated with Charles' law. Let's just say graphs of Charles' law. Charles's law. All right, so graphs of Charles' law. So we're going to look at two sketches. So let's do that. So let's say we sketch out two axes like so. And for this one, I'm going to allow this one to look like that. All right, so these are my two axes. And I'm going to be inserting some information. All right, so we know obviously the vertical is the y, horizontal is x. So let's say for this graph right here, the graph on the left, we're going to plot, because again we're looking at Charles' law. And we're looking at the relationship between volume and temperature. So for this graph, let's say we plot the volume on the y-axis in cubic meters. All right, the volume in cubic meters. And before I continue, you will notice that I did not include the units, right, for these variables. And again, the volume can be in any appropriate unit. We know the SI unit for volume is the cubic meter, right? But we can express volume in any appropriate unit, whether cubic meter as SI unit, or centimeters cube, or liters, right? Or what else we could use for the volume? dm cube, right? Milliliters, any suitable unit. However, we have to ensure that the unit that we have for V1 is the same as V2. Once that is the case, you're okay. All right? Because in most cases, what will happen is that the units will actually cancel out. Right? But as you know, if you're explicitly required to express in SI unit, then if you do the calculations in, let's say, cm cube, at the end you have to remember to do your conversion. Right? However, for the temperature strictly must be in Kelvin. Temperature strictly must be in Kelvin. All right, so in this case now, we're plotting volume in cubic meter on the y-axis, and we're going to plot temperature in Kelvin. So, if we plot volume against temperature for a fixed mass of gas, assuming that we keep the pressure constant, we should see that the volume and the temperature will show a directly proportional relationship, right? So then, how do we represent that on the graph? How do we represent directly proportional relationship on the graph? Straight line through the origin. So we're just going to draw a straight line like that. And that's what we're going to get once we plot volume against temperature in Kelvin. Right? So you should be able to sketch this graph one, and you should be able to identify, right, which law it is used to investigate. Because again, if you see volume and temperature, you know that Charles' law is what deals with volume and temperature. So you should be able to identify the law based on the graph. And you should be able to sketch the graph if you're asked to do so. Now for this one now, we're going to be plotting volume on the y-axis. So this is V in cubic meters again. But on the x-axis, we're going to plot temperature. However, we're going to use temperature measured in degrees Celsius. Right? So we're plotting volume against temperature, but the temperature is in Celsius. Right? The temperature is in Celsius. And we're going to sketch the graph, and then from the graph form, we're going to discuss and see, okay, what is the relationship between the volume and the temperature in Celsius. In Celsius, we know for temperature in Kelvin it is directly proportional, but we're going to see what happens when the temperature is in Celsius. All right, so before we do that, let me ask this question. When we have a fixed mass of gas at constant pressure, right? Let's say we're keeping track of the temperature in degrees Celsius. As we, let's say, change the volume of the gas, right? As we change the volume of the gas, let us say, we have a container with some gas where we can change the volume. And by changing the volume, we might compress the gas, right? Or we might allow the gas to expand. So let's say that we're able to compress the gas such that the pressure is not changing, right? Let's say we're able to do that. Would you expect that when you change the volume, the temperature would increase? If, let's say you increase the volume, would you expect the temperature to increase or would you expect it to decrease? Increase, okay? You'd expect it to, anybody expect it to decrease? So if you increase the volume, would you expect the temperature to increase? Decrease? You go increase, okay. But would that increase be such that it shows that they're directly proportional? Huh? Alright? Again, we're just putting our thoughts out there. Right? We're going to cement what actually happens. But just to have the discussion going, we're just putting our thoughts out there. Right? So again, Roger would have stated that, okay, because the volume is directly proportional to the temperature in Kelvin, you're saying that, okay, if you increase the volume, you'd expect the temperature to increase as well. But it may not show directly proportional relationship. Okay? So in other words, if we increase the volume by 2, the temperature might not necessarily increase by 2 as well. Okay? Because if they're directly proportional, as we see right here, if we increase the volume by 2, the temperature will increase by 2 as well. Assuming that we can keep the pressure constant. Okay? So for this one now, once we have volume against temperature in degrees Celsius, we're going to get a graph that looks like this. Alright? Where it shows that the volume is proportional. Right? Because again, we get a straight line. Right? Once we get a straight line, it shows proportionality. Right? The difference between these two now is that this one, it starts at the origin, where the origin is 0. So once you pass through 0 and you get a straight line, it means that they are directly proportional. But for this one now, it's just proportional. Okay? So let me show the 0 point. So 0 right there. 0 right there. So that's our graph. Now it turns out, at some point before I would have shared with you a certain number when you are converting between Celsius and Kelvin. But do you remember what that number was? 273, right? 273. Now it turns out that we can actually obtain that value from this graph right here. Okay? Because if we were to just extrapolate the graph, or in other words, just continue the line until it reaches the x-axis, we're going to get a certain value. And what would that value be? We're going to continue the line, and we're going to touch the x-axis, and we're going to obtain a certain value. What would that value be? Remember that number? Negative 273, right? 273, but it's going to be negative because it's on the left-hand side, right? So if we trace it back like that, right, we're going to get that value of minus 273, right? We're going to get minus 273, right? And it makes sense, right? Because again, remember, here, when the line starts at the origin, the temperature is 0 Kelvin. But here, we have minus 273, and again, this would be degrees Celsius. And this is the lowest possible temperature, first of all. And remember, if we want to convert from Celsius to Kelvin, remember we add 273. Okay? We always add 273. So, that's what we see right there. So this is how we can actually obtain the Kelvin scale using this graph right here. So you should be able to, again, sketch this graph in an exam. right? Or even to plot it, because I've seen cases, where you are asked to plot a graph, and the graph will actually come out like this, and oftentimes persons are not aware of this particular graph. So this is what we will see. So we're going to look at some examples after you take that down, yes? Yes, exactly. So see it here. Because when you add 273, you're going to get 0, because minus 273 plus 273 is 0, which is 0 Kelvin. Right? So this right here is 0 Kelvin. Right? Yeah, but again, Celsius. This 0 right here is in Celsius. Okay? But if you want to get the Kelvin, as I said, you add 273 and you're going to get 0 Kelvin. Okay? So that's that. Any other question? Alright? Daniel? Make sense now? Right? So we're going to clear it up, right? Just wanted to have the discussion, so we can identify what are our thoughts. Okay? So we'll look at some examples, and we've got one example on the board, and I will just give you one to work on so we can move into the pressure law, and then we're going to put all the laws into one. Alright? So, example time, right? Example. Alright? So, let's say, just write to this one. Show the black. So, let's say that a fixed mass of gas is held, or let's say is kept in a container of volume. What will be the volume of the container? Huh? What will be the volume of the container? 123? 43, okay. 43, let's say cm cube. Alright? Can I use 45? Right? 45 cm cube. Alright? And what's the temperature? What's the temperature, Savannah? Give me a number. 75? Alright? 75 degrees Celsius. Alright? 75 degrees Celsius. Now, the gas is cooled to, let's say it is cooled to 20 degrees Celsius. The gas is cooled to 20 degrees Celsius. Determine the new volume, assuming what? Assuming what? Pressure is constant, right? The pressure is kept constant. Alright? So that's what we have. So we're given this scenario right here that we have a gas, a fixed mass of gas in a container, and the volume is 45 cm cube. Right? And the temperature is 75 degrees Celsius, and we're cooling the gas, or we cool the gas so that it's now at 20 degrees Celsius. What is the new volume? Right? And we would have ensured that the pressure was kept constant. So since that's the case, then we can apply Charles' law. Right? We can apply Charles' law because Charles' law would be applicable in this scenario based on the condition that the pressure is kept constant. So to work that, we start with this expression right here. So we're going to say what that side. So we can say that V1 over T1 is equal to V2 over T2. All right? Right over here. Because some persons, might not see down that side. So let's just note some information that we have. So V1, what's V1? Right? It's 45 cm cube. And V2, what's V2? What's V2? Unknown, right? We did not get V2. So V2 is our unknown, like that. T1 now, 75. What's the unit? Degrees Celsius, right? Now, this is the point, where we have to stop and check ourselves. Because again, we said that the temperature in Kelvin. So then, we're given the temperature in degrees Celsius. So we have to convert it, right? So we can do the conversion right here. So we add 273, and that becomes what? Yes, 348 Kelvin. Good? And in T2 now, what's T2? 20, right? So we say 20 degrees Celsius and we add 273. That's going to give what? 293, right? So we always want to do that. Right, so we have T1 and T2 in their appropriate units, so then we can now start to calculate. Now because we're trying to find V2, we can just simply multiply or bring T2 up that side and then we're going to get V2 right there. So V2 then now, right? Are we comfortable with that? No. Right? So because we're trying to find V2, we're basically multiplying both sides by T2, multiply by T2, T2 cancels right there. Multiply here by T2. So in short, the T2 comes to the top right there. Okay? Yes. Yes. So that your temperature can be in Kelvin. No, it wouldn't be negative, because again, we're adding 273, and the number that we start with is a positive number. So if we're adding a positive number to a positive number, you're going to get positive. But if it was like, let us say, minus 300, right? And you add 273, you're going to get, that's what, 27, negative 27, okay? So V2 then now. So V2 is V1 times T2 over T1. So we have all the values that we have, so we can just plug in now. So 45 cm cubed times T2, which is 293 Kelvin, divided by 348 Kelvin. If we are comfortable with just using the calculator, we can just plug that in, one go, and get our answer, or we can work the numerator, write it, and then divide by the denominator. Right? And note that we're going to have some cancellation going on. So the kelvins cancel out. So our answer, because it's volume, is going to be a unit of volume. In this case, centimeters cube. Anybody work this out? Is it? 36? Okay. So 36.2 cm cube. Okay, can look at an example like that, right? Look at an example like that. So we're going to get 36.2 cm cube. Somebody get something different? Double check it for me, please. Yes, 348. 37.887. 37.8. Okay. Are you more person getting 37? All right. So 37 point how much? 89. So that's like 37.9. So 37.9 cm cube. All right. So notice where we saw that in this case the initial volume was 45, initial temperature was 75. We cool it to 20, right? So we decrease the temperature. So we expect that the volume should also decrease, right? So expect the volume to also decrease. No, it's directly because it's Kelvin. Kelvin. Temperature in Kelvin. Well, if we're talking about Celsius, yes, so no. But if it's Kelvin, no, it's going to be directly, right? So yeah, good point. So again, just to clear it up, because we're looking at the temperature in Celsius, we're not going to see that directly proportional relationship. Okay? But if we express in Kelvin, we're going to see a directly proportional relationship. But at the very least, we should see that if we decrease the temperature, the volume should decrease as well. All right? We're going to look at an example where we're going to be able to more clearly see that direct relationship. So let's try another example before I give you one to work on in your books. So let's do this. So let's say another example. So let's say 25 cm cube of a gas is held in a sealed container by a movable lid. All right? The gas is initially, let's say the gas is initially at 27 degrees Celsius. All right? The gas, you said that you wanted a temperature one, right? To find temperature. All right, so let's try that. The gas is heated. All right? And the gas is heated. All right, I'll leave off the is again. So the gas is heated. And its volume increases to, let's say, double of that, so 50 cm cube. All right? Calculate the temperature of the gas if the pressure is kept constant. All right? So that's what we have. All right? So that's our scenario. We have some gas in a container with a movable lid, right? And the movable lid is just to facilitate the volume of the gas changing. So we heat the gas and the volume changes so that the volume is now currently twice the initial volume. Okay? So we essentially see that the volume is now doubled. Right? So then we expect the temperature to also double. Right? Now in this case we're asked to find the temperature, right? In this case. So therefore now because of that scenario, we can just simply say that okay, the temperature is going to be just double of this, which is 54. Double this, right? Just double this, right? Yes? Just double it? Why? It's in Celsius, right? So because the temperature is in Celsius, it's not going to be directly proportional. It's going to increase, but it's not going to be directly proportional. The double that we see now is going to be in terms of the Kelvin, right? So if we are able to express this in Kelvin, and we double that value, then that's going to be the final temperature. But we're going to do the work, to actually verify it. Yes. Do you understand? Okay. Ask the question. Why don't understand? Why? Because again, it's only directly proportional. It's only directly proportional. Hold on. Alright, it's only directly proportional when the temperature is in Kelvin. But in this case now, this is degrees Celsius. So it's not going to be a double. Okay? If this was Kelvin, then it would be doubled. Okay? There was a question over here as well. What's what? This? We're transposing to find V2, right? Chevelle? We're showing that the T goes up here, right? By the process of transposing. So we multiply both sides by T2. This T2 cancels off this one. But because we multiply one side by T2, we have to also multiply the other side by T2. So we end up with T2 basically changing its location. Right? Just don't write it then. Right? Alright? Then don't write it then. Alright, so let's go again. So we're going to do the working out here. So again, we're using Charles' law. So we're going to write the formula. So V1, no, it's an example. Alright, let me get one on the board. T1 is equal to V2 over T2. So again, V1 is 25 cm cube. V2 is double of that, which is 50 cm cube. And then T1 is 27 degrees Celsius, which again we know we need to convert. So we add 273, which is 300 Kelvin, and then T2 is an unknown value, which we're going to now determine. So we're not going to do the calculation now. So we're going to say, again, we're trying to find T2. So we can do some transposing. So let's do the transposing. So we're going to do a cross multiplication. So I'm going to do it the long way. So we're going to get V1 times T2, hold on a second, equals V2 times T1. Yes. If you want to go from Kelvin to Celsius. Okay? Yes. Yes, you can go. So when we cross multiply, the T2 multiplies V1 and the T1 multiplies V2. So we get this right here, but again we're trying to find T2. So we can divide this one by V1, divide this one by V1. So we see this cancelling that. Huh? Repeat? Okay, so the first thing we do is we cross multiply, right? So this denominator, T2, will multiply V1, right? And this one multiplies this over here. So we get this statement right here, that V1 times T2 when we bring it up is equal to V2 times T1 when we bring it up and across, okay? Now we're trying to find T2 because that's our unknown. So because we have V1 times T2, if we can somehow cancel off the V1 so that we're left with T2, then we're one step closer to getting to our goal. So we do that by simply dividing by V1 so that they can cancel off, but once we divide one side by V1, we have to do the same thing by V1 as well. So we get T2 now is equal to, which is what I'm going to write here. So we get T2 is equal to V2 times T1 over V1. Now, T2 now is V2, which is this value. So 50 cm cube, divided now by 300, which is T1, 300 Kelvin. And what do we get for this? We said it's going double, so 600, right? 600 Kelvin, right? And you can verify it on the calculator, right? Sorry. Right? 600 Kelvin. So we see the relationship, okay? Notice that we made a mistake right here. Yes. This should be T1 right here. Yes, brilliant. Yes. So this is 300. Answer is still going to remain the same. Right? And V1 is 25. Right? Still going to get 600. Yes. It's just that, because I was, I guess, focused on getting the answer, I just start write up some stuff. No. No, it's transposed correct, It's just a substitution. I messed it up. I didn't put T1 right there. So, All right, so that's what we get. All right, so we're going to look at a question here. Yeah, I mean, I'm just trying to do two things in one with this question. So let me just go with it. All right, so the diagram shows the setup. Listen up, students. The setup, if I say it spell it, setup of an apparatus to investigate Charles' law. Right? The gas was initially at 25, and let's use 20, or 24 degrees Celsius, and its volume was let's say 0.18 cm cube. All right? 0.18 cm cube. This is, you know what it? Yeah, mine. 0.18 cm cube. So we're going to sketch the diagram that we would normally use to investigate Charles' law. All right, so let's do it this way. So we're going to have something like this. And we're going to have some, let me put the water in last. No, maybe some right-handed and some left. Yeah, so just give me a minute. So let's say, we have that. So we're going to have this with some water. All right. We're going to have a little seal right here. All right, so we have a little seal right there. All right, something to trap the gas. Right? Something to trap the gas. And then we're going to have the gas here. All right? Now, we're going to have a thermometer inside here, so let me just sketch the thermometer as well. Let's sketch the thermometer. All right, so that's a thermometer. And the temperature is, let's say the temperature is 40. Let me just put it right here. T equals 40 degrees Celsius. All right? And I'm going to, no, it doesn't come from lunch. We're on a 5-minute break, boy. So let's say that the height of this is let's say 2 point, let's use our whole number. 3 centimeters. Right? 3 centimeters. Now, I'm gonna add something here as well. The gas was held in a capillary tube. I'm going to make this a little easy for you, of radius, let's say 0.4 centimeters, right? And the pressure was kept constant, yes. All right. Oh, do I want to do that? All right. No temperature. All right, no temperature. Because we want to find the temperature. So calculate. Because I gave it a lot of information, so I have to take back one. Temperature of the gas. All right, so we're essentially accomplishing two things in one essentially. I'm going to also label this up because a part of your syllabus is you should be able to sketch the diagram to investigate Charles' law. All right, so I'm going to label this up for you. Choose the black. All right, so this is, we're going to have some water inside of this thing right here. Something like that. All right. So this right here is our water bath. All right. This right here, it's a plug. We usually use sulfuric acid or mercury. Right? So I'm going to say amino mercury, right? Just to trap the gas. This right here is a thermometer. This right here is our trapped gas. And then these now would be our gas molecules. Sorry. Yeah, but you know. No, but assume that you can see it. Right? Yeah. And this is our capillary. Capillary. Alright, so again, as I said, while you're working this question, you're also being familiarized with the diagram to investigate Charles' law. Right? Yes, to draw it, right. Or even label it. Yes. Alright? Again, remember you have to start off with the formula, right? And verify that you have all the relevant information to perform the calculation. Remember, the capillary, the gas trapped in the capillary will resemble something looking like this. Right. Alright? So the trapped gas in the capillary will look something like that. Yeah, the trapped gas, right, will resemble a cylinder. Huh? Pi r squared. Right? But remember it's a cylinder, so it have a long side. Right. Right. Okay? That's why I gave you the height right there. So, as you know, sometimes in the exam, the information will be in front of you, right? But if you're not sure of the approach to take, you might think that, okay, the question is more difficult than it is, yes? The gas, is it? No, man, remember, I take off the temperature. Because when you find it, right? When you find it, remember, so just a 14, what if it's not 40? Right? This is the initial temperature, right? So the temperature before the start of the experiment was 24, and this was the volume, right? And then after the experiment, we have this scenario, and we want to find the temperature. Okay? Yeah, okay. All right, so for the others who haven't marked your book, we're going to just hold off on that because we want to move into something different. So let's continue. All right, so we're looking at Charles' law. Now we're going to move into the other gas law. That is it. But it should have this by now. All right, so let's go right into this. So we're going to talk about the pressure law. Students, listen up again, listen up. We're going to go into a new topic. The pressure law. All right? Pressure law. And Boyle's law would have looked at volume and pressure. Charles' law would look at volume and temperature. So what else have we not, or what have we not looked at as yet? Temperature and pressure, right? So the pressure law as it says, the pressure law deals with pressure and temperature. Right, and again, as we said, students, let's go again. And again, as we said, we always will start off the gas law with a statement that says that, okay, we're dealing with a fixed mass of gas, right? So the pressure law, let's start it this way. So this states that for a fixed mass of gas, at constant volume, right? Because if you're looking at pressure and temperature, the other quantity is the volume, and we're going to keep the volume constant. At constant volume, the pressure of the gas is directly proportional to what? To its what? The mass is fixed. To its what? Again, pressure and temperature. What? Huh? The volume is fixed. The volume and the mass is fixed. Right? So we're looking at the relationship between the pressure and the temperature. So we're saying that for a fixed mass of gas at constant volume, the pressure of the gas is directly proportional to, but remember, once we're talking about gas laws, the temperature must always be Kelvin, right? Kelvin. So we say it's absolute. So always remember that. Absolute / Kelvin temperature. And that's the pressure law. Alright? That's the pressure law. So, that's the pressure law. And again, we can write the expression. So, we say that the volume is fixed and the pressure is directly proportional to its temperature in Kelvin. So, we get V is directly proportional to, sorry, not V, P, my bad, P. So, P, which is the pressure, is directly proportional to the temperature. So, again, we can write P is equal to K times T. And again, dividing both sides by T, we get P over T is equal to K. Right? Which summarizes the pressure law. So in this case, we're saying that the ratio of the pressure to the Kelvin temperature is a constant. So we get P over T is equal to K. And again, always remember, once you hear the talking about gas laws, just make sure the temperature is in Kelvin. If it's not in Kelvin, convert it, right? Because if you do the calculation with the temperature in some other unit other than Kelvin, you're going to get an incorrect or a wrong answer, all right? So, with that being said, now we can write P1 over T1 is equal to P2 over T2. So this is what we're going to be using to do calculations. All right, and again, we're going to look at some graphs as well, real quick. All right, so that's the statement. So let me just sketch the axes in the meantime. So, graphs. I'm going to give it time to take it down. I just want to keep the flow. Graphs of pressure law. All right, so let's do the axes. And you're going to see that for this one, the graphs are going to look similar to the ones that we drew before, the one that we sketched before. We're going to get something similar, all right, something like that. All right, let's put the origin right here. Origin like that. So, for this one, we're plotting pressure instead of volume, measured in Pascal against temperature in Kelvin. So just like we saw with Charles' law, we see that for the pressure law, the pressure is directly proportional to the Kelvin temperature. So if we plot pressure against Kelvin temperature, we would expect to get a directly proportional relationship. So we're going to get straight line through the origin just like that, right? And in this case now, if we plot pressure in pascals against, this is what now, temperature in degrees Celsius, we're going to get graph looking similar to the one for Charles' law, right? So we're going to get the proportional relationships or something like that. And again, if we trace back like that, minus 273, right, degree Celsius. Yes? Huh? Yeah, because it's a different graph. So that's what we see, right? So again, the main thing with the pressure law is the fact that we're looking at pressure and temperature, right? And they're directly proportional. So when you're studying these gas laws, you always want to remember what is being investigated for each of the gas laws. So Boyle's law is volume and pressure, right? Boyle's law is volume and pressure, and we state that the relationship is inversely proportional, right? For Charles' law, it's the volume and the temperature, and they're directly proportional. And for the pressure law, it's pressure and temperature, and they're also directly proportional. So once we can remember that, we should be able to recall the rest of the statement for each of the gas law. Okay? Right? So that's that. And we're going to look at an example, and then we're going to look at the combined gas law. What's the time? 2:30. Okay, so we have a look at time. All right. All right, so example. Let me write it on the board in the meantime. Example. Huh? Yeah, it's long. Yeah, long time. All right. So example. Let's see. All right. So we're gonna say that this one, a sealed cylinder of gas at, well, let's say initially, hold on, let me see. May I come back? Warren, go, you can go. Initially, at, when one comes back. Initially at a pressure, quiet down guys, quiet down. A pressure of kilopascals and temperature of, let's say the temperature is 32 degrees Celsius, is, students, we want to be taking down the example. 32 degrees Celsius is heated to, right, heated to 100 degrees Celsius. Determine the final pressure, right? The final pressure, and we're going to say categorically that the volume, the volume is kept constant. Let me just go with that. All right, so that is our example. That's our example. All right. So let me just give you some time to take that down so that once you start going through, you're able to pay attention. Arona, you finished copying down the question? Okay, so start working it out. Yeah, it's an example, but I think so it'll be, you know. All right, so let's go. We're gonna work through this now. So, again, students, Roger, Neela. So, again, Ariana, mind that we don't always say, when you feign certain things, it might become permanent, so careful. Alright? Alright, anyways, back to the thing. So in this case now we're told, listen up students, that the volume is kept constant. And when we're working questions, because in the exam, you're not going to be explicitly told which of the gas laws. In the examples that we're doing, when we were looking at Boyle's law at the time, the only gas law that we know was Boyle's law. So obviously the example would require us using Boyle's law. Earlier, when we started looking at Charles' law, the example, again, because it was associated with the topic, it would have been Charles' law. And similarly, in this case now, we know automatically it's going to be pressure law. But in the exam, you're going to have to determine which of the gas law to apply. So one thing that you always want to look for when determining which of the gas laws is what is kept constant. Right? What is kept constant? So in this case now, the volume is kept constant. So I could say, instead of saying that the volume is kept constant, I could have said that, okay, the cylinder did not expand, right? Or I could say that, a sealed cylinder of fixed volume, right? I could say something like that, right? So I could use other statements that would suggest that the volume is constant as opposed to just stating it categorically as we did right here. So in the question, you always want to look out for those things, okay? What is kept constant. All right, so in this case now we're going to be applying the pressure law. So we start with P1 over T1 is equal to P2 over T2. All right? Now for our purpose, P1, what is P1? Kilopascal. Right? And P2 is what we're trying to find, so that's unknown. Right? T1, what's T1? 32 degrees Celsius. Right, so we're going to add 273 to convert it to Kelvin, so some 5 must be in there. Right? So 305 Kelvin. And then T2 now is 100. And we add 273, so we get 373. 373. Alright, Kelvin. Alright? Now that we have all the information that we need, we first have to do some transposing and then we find P2. So we're going to simply take the T2 right here, bring it up to the top, right? And as such, we get, right? Yes, so we get that P2 is going to be equal to P1 times T2 divided by T1. Now, we have to now appropriately substitute the values. See there? We just move that up, right? So now, we plug in the values here now. So P1 is 220 kilopascal. T2 is the 373 Kelvin. And then T1 we say was 305. Alright? Kelvin. Alright, yes, so we cancel the K's. For the Kelvin, that is, not for kilo. So, students, note, this is the unit Kelvin. This is the, what we call him something again? The K, what we call the K? As a group, what we call him? Prefix, right? So the K is kilo, which is a prefix that is placed before the unit. So, yes, you can have millipascal, right? You can have micropascal, you can. 269? 0.05. Okay. So 2.6, use the black one done. So this one we say now is 269. So let's say 0.1. And its pressure, so it's going to be kilopascal. Oh, I see what you're saying now. Okay, Daniel. Alright? 269.05 kilopascal. Alright? So, that's that. We're going to next look at the combined gas law. What's the time? Yeah. 246. All right, 246. All right, so last 10 minutes we're going to use that to talk about the combined gas law. All right, so we're going to now move into the combined gas law, or also referred to as the general gas law. You have to move speed, Ariana. The general gas law. Alright? The general gas law. So the general gas law, gas law, combines, hold on, Daniel, let me just write this. Combines all three gas laws. Alright? All three gas laws. Right? We can express the general gas law using what we call now the general gas equation. So everything is involved. So nothing is kept constant other than the mass. General gas equation. Alright? So, the general gas equation now, let me put our subheading. So the general gas equation. Roger, you're taking down this information. The general gas equation, we write it as PV over T is equal to K. Right? So PV, K is the constant, right? So PV over T is equal to K. Everything is involved. Right? Now we can expand on this equation right here as P1 times V1 over T1 is equal to what? P2 times V2 over T2. Right? So this one on the right, Ariana, this one on the right is what we will use when we are Akila and Roger. This is the expression we use when we have to perform calculations in which we have all three variables changing. So the gas law the general gas law, sorry, is used once we have all three variables changing. So once the pressure, the volume, and the temperature, they're all changing, we use the general gas equation, or sometimes referred to as the combined gas equation. Alright? Now we're going to, how we stay on time?
7 minutes.
Okay. So let me just note the units right here. So for this one, P1 and P2, right? Can I see it? Okay. Let's use the black. So P1 or P2, right, can be in any, yes, any appropriate unit of pressure. So whether Pascal, kilopascal, right, millimeters of mercury, or even PSI, pounds per square inch. PSI. While T1 and T2, so let me do V first, so I'll do the T them last. So V1 and V2 can be in any appropriate unit for volume. So whether cubic meter, cubic centimeter, liter, right, etc. While, hold on, T1 and T2 must be in Kelvin, right? Must be in Kelvin, right? mmHg, millimeter mercury. mmHg, millimeter mercury. Okay. mHg, because the symbol for mercury is Hg, so it's millimeter mercury. Hg for mercury. Alright? Millimeter mercury. So that's where we leave it today. Alright? That's where we leave it. Any question? So we have now completed our look on the gas laws. Right? So we look at Boyle's law, we look at Charles' law, we now look at the pressure law, and we show that we can actually combine all of them into one. Right? Yes. PSI, pounds per square inch. Right? Pounds per square inch. Alright, so that's that. Alright students, so that is it. That is where we are going to end today's session.